Okay, and to finish, now we have this motional EMF thing happening. It looks like there's quite a lot going on with this, which seems to be the theme this year. So, this is a typical problem type, but there's a couple spins on it. So, we got some conducting loop that's basically flying into a B field. Its flux is going to increase, stay constant for a little bit, and then decrease, stay constant. That's what it looks like, at least. So this is a very common question of motional EMF. Let's see what we're asked. A wire is connected to a resistor of resistance R to form a rigid rectangular loop of width L and height 2L. An external force is exerted on the loop such that the loop always moves with constant speed in the plus x direction. Uh, the loop is approaching this field of external magnetic field. It's into the page. And then it eventually goes all the way through and comes back out. On the following axes, sketch a graph of the magnetic flux phi through the rectangular loop as a function of position x of point S, which is on the right side of the loop. So again, just like with all things with Physics C, we typically like to do the graph just by plotting points and then figuring out how they connect. So, to begin, well, S definitely starts at 0. There's no flux in the loop originally. And there's also going to be no flux in the loop when we get here, which is 3.5 L. Or sorry, that's also when we start to, there's also no loop, no flux when we get here, sorry, at 4.5 L. Because again, that would be this. So our graph is going to start at 0 and it's going to end at 0. So now let's see what's happening in between. So the first time where the loop gets in contact with flux is at x equals L. So that means nothing interesting is occurring from 0 to L. But then, as the loop enters the field, it's slowly going to collect more and more flux as more and more of it sneaks in until eventually the whole thing is covered. So once S gets to 2L, all of the loop is inside. So we're going to build up negative flux at a constant rate when S is equal to L, all the way up until S is equal to 2L. So from L to 2L, it builds up flux at a constant rate, and it's in the negative direction. Let's see, can I make that slightly straighter? Third time's a charm. Yeah, nice. Okay, and what's the magnitude? So it says to... it doesn't explicitly say it, but I think we do need to include it anyway, what this value is. Well, what's the maximum flux through the loop? Well, it's... let's see, the max flux is going to be the B field times the area, which is the B field, and then we got a 2L by L loop, so 2BL squared. And it's negative. Okay. We've reached 2L, so now the entire loop is in, and there's no change in flux up until it reaches this boundary. So from 2L to 3L, it's constant. All right. And then, as we move to the right past there, so 2L, 3L, Or sorry, it's 2.5L. It's to 2.5L before we reach the boundary. So when point S gets here, we're still all the way in. But then, after that happens, this is a net sort of decrease of flux because the flux is going to cancel out above and below this midline, whereas it had flux before. So its flux is going to decrease at a constant rate up until 3.5L, which is when it leaves the region. So we get this as our shape. Very tricky. Consider the instant when point S reaches x equals 1.5L. Indicate whether the current in the loop is clockwise, counterclockwise, or zero. Well, let's see. X equals 1.5 L, so that means we are half in, half out, basically. So, notice that at this moment in time, more negative flux is being added to the loop. Again, it shows that in the graph. We didn't really need to look back here. So, what this means is that phi is growing into the page. So again, anytime we have an induced field or a Lenz's law situation, say, what way is the flux changing? So this means that B induced must generate phi out of the page, right? Get the flux out of here. So if phi is growing into the page, the loop says get the flux out of here, and it goes the opposite way. So we need a B field to generate out of the page flux. So by the right-hand rule, that means I induced has to be counterclockwise. Derive an expression for I through the resistor when point S reaches that point. So this could be quite tricky if you're not that familiar with motional EMF. This is kind of hard to do directly with Faraday. I'll show a couple ways of doing it. But we know that by Ohm's law, we know that the current is just going to be the EMF that's induced divided by R. Okay, so we got to figure out what that induced EMF is. So by Faraday, we know that induced EMF, in magnitude at least, is going to be equal to d phi dt, which is going to be equal to d dt of B times A. And well, let's look here. So if we look at our loop and go back up here, the effective area is changing. So there's always going to be this height. There's always going to be this height that's in the region. It's just a matter of how much of the length is in the region. So this length would be called x, and this is still 2L. So the rate of change of the area is just going to be 2L times dx dt, which we know as a velocity. So E induced is equal to B times 2L times dx dt, which is equal to 2BLV, because dx dt is defined to be V. So we get I across the resistor, I through the resistor is 2BLV divided by capital R. That's not the only way of doing it. The most clever way I've seen to do this, which I find quite neat, is the chain rule. So I've also seen this done via a chain rule where d phi dt is equal to d phi dt. Well, again, if you do a dummy variable with the chain rule, you get this done. So d phi dx times dx dt. So how does phi change as a function of x? Well, that's just going to be b times 2l. Because again, phi is going to be b times 2l times x. And what's dx dt? That's just v. Nice, works out. And lastly, derive it, or sorry, we still got more. Not lastly, not yet. Derive an expression for the power P dissipated by the resistor. This is easy. It's just P equals I squared times R. And oh look, we found I. Done. There's no way that's more than 1 point. All right, and now the boundary between the field canceling region basically got shifted left. And we're asking whether the total energy dissipated is increasing or decreasing. So notice what's happening this time is the changing flux region is smaller. So it's still going to be increasing flux at the same rate, but it does it for less time. So what that means is that in this case, we have same d phi dt for less time. So if we're inducing an EMF, the same one for the less time, so what this means is that the integral of I squared R decreases. So power, this is power, decreases since t decreases. So what this means, same d phi dt, which means that we get the same I induced, but just for less time. So the new power is less. So that's kind of tricky. Because again, what's happening here is that I get all this distance to increase my flux. But if I decrease my flux changing region to this part, well, I'm doing the same induced current, but just for less time. So I can't generate as much power. And then, because why not? It's a triangle now. I thought this was quite challenging. So it's the same thing, except now it's a triangle instead of a rectangle. So we want to sketch a graph of the induced current as it moves into this region fully. So what we should notice here is that if it just barely gets in the region, it's sweeping sort of a small amount of area. But if you're just barely entering at the edge, well, you're going to be gathering a large slice of area. So our graph of phi, which we're just going to do kind of a side here, phi is actually going to increase kind of like a parabola up until a point, and then it becomes constant. So let's see, when is that? So, well, if this is L right here, that's when the loop is fully in. So the flux change stops once the corner of the loop has reached 2L. So that actually means our induced current is 0 anywhere after 2L. And it's also originally going to be 0, and then it starts increasing. So if this is our graph of phi, we know that I of t is going to be proportional to d phi dt. So if the if the flux is quadratic, then that means the induced current is going to be linear. So we got some sort of piecewise thing happening here. And that is the end of E&M, set 1. Now that is a tough question. I have no idea what the average score on this question is. I think it is going to be quite low. This is really freaking hard.